Our next speaker today is going to be Medha Sharma, thank you, from Toronto University, who is going to talk about cytoskeletal patterns in Drosophila embryos.
Yeah, well, it's good morning. So, good morning, everyone, and welcome to the last session of this mini course. And as I just mentioned, I'm Medha from the Department of Cell and System Biology in Professor Harris' lab at U of T. And first of all, before beginning, I would like to thank Anna for extending this opportunity to discuss my work with you all. And as I move forward, I will be discussing I will start with discussing some basic biology of my system so that all of us understand what's going on actually inside the animal. And then I will move on to discuss the formulation of my mathematical model. And finally, I would like to share some of the challenges that I'm facing in mimicking the actual dynamics of the in vivo system. So to begin with, throughout this course, we have been seeing various beautiful patterns in the bacterial culture and in the biofilms. So we are all aware that there are certain theories which are in the literature for quite some time now that are capable of explaining certain pattern formation. Especially the Alan Turing theory, it's around since 1950s, and it's a very simple theory that is capable of explaining a range of patterns ranging from patterns on the animal skin to patterns in the deserts on the sand, and it can explain it all. And people have developed various beautiful mathematical models that are able to recapitulate these patterns. But the interesting part about this theory is that this is a self-organizing pattern because you have chemicals that randomly diffuse around, react with other chemicals, and form these patterns. However, when we talk about patterns that are pretty repetitive in nature, for example, the body plans, so all of the humans and other species, they have a very specific body plans. We have our eyes where they should be, our nose where it should be, 5 fingers, and stuff like that, which are very repetitive. So when it comes to such repetitive patterns, a simple random diffusion is not enough to explain it. So then we will move on to what is called as positional information model, in which we assume that there are certain cues that are already present in the system that define where the pattern should be forming. So for example, if I talk about a fruit fly, then in the case of its embryo, even before the egg is fertilized, there are patterns, chemical cues that decide that if ever this egg will get fertilized, it will have its head in this part and it will have its abdomen in the other part. So, but the interesting part is like that both these models are depending on chemical signals and chemical interactions. However, the model of pattern formation that I'm trying to study is the one which deals with actual physical relationship, like physical interaction between chemicals that can lead to pattern formation. Now, lucky for me, Drosophila is a very good model for studying pattern formation because throughout the embryogenesis, there are various stages, and in all these stages, there are beautiful patterns that are formed. But my research particularly focuses on very, very early pattern formation in very early development cycle. And what happens in this very early cycle is that there is just one big egg, and this one egg is just fertilized. So it is only a single cell with a lot of number of nuclei. So nuclei are dividing inside this single cell, and with each cycle of nuclear division, what happens is the nucleus, it signals on its top to form an actin network. And this actin network, we call it a cap because it's like a cap sitting on the top. So we call it actin cap. And the remaining of the cell is filled with another network that is the actomyosin network. Now, the thing that we want to know simply is that this network is expanding material, so it expands outwards, while this other material is contracting material. So it has a tendency to contract on itself. And this is the view that we get from the top. But if we want to look at the side, what we see is that we have these nuclei, and these nuclei are basically having an actin cap at the top and a myosin network at the side. So if I just look, what happens after like a few seconds is that there is an interaction between these two networks. So these two networks physically interact in some way that we don't know what happens, but this interaction makes a bending, a buckling in the two materials, and this buckling leads to membrane bending and forming this compartment. Now the interesting comparison, rather a funny comparison that I would like to make, is that we can compare this to a simple egg tray. So what happens in the egg tray is that we can put our eggs here, and our eggs would be particularly safe here, because if we move them, then they do not smash into each other, and that's why we keep them in this particular shape structure. So what is so special about this structure that keeps them safe? And as for me, I think that is these grooves. So I have a prop here to show that there are these grooves where we can keep individual eggs. And the speciality of this is that it makes an individual compartment for each egg. Exactly the same thing is happening here. These individual nucleus are safe from each other because there is a membrane in between. So it prevents from colliding and mixing their material with each other. Now, interestingly, if we look at this from this side, so the orthogonal view would be these circles, right? So if I image this structure, it would be having circles as well. But so what is the purpose of it? Is like now this is we are just looking at the nucleus, and what we see here is that there are a number of them, and by preventing them, what we are doing is like we are preventing the undifferentiated progenitor cells, because these cells are the cells which will later on form the whole body. So if they are damaged, we will have an abnormal body. And so when we look at from the orthogonal side, what we see is these patterns, which is obvious that these circles will appear. However, there is a big difference between the prop and this actual system, that this is fixed. Nothing is happening here. But here, these are actually being generated and disassembled after each 15 minutes. After each 15 minutes, we see that they start to form, and later on they just...
That's the question. In the image, the dark spots are the nucleus?
Yes, exactly.
And the thinner one are the actin myosin.
Exactly, yes. So that's what the interesting part is, like in the beginning, they are very rough. And as we keep on, like we see for around 150 seconds or so, something like that, in 2-3 minutes basically, we see that they have a very sharp curvature and a very sharp boundary.
May I have another question? Earlier you said that there are, no, even earlier, keep your image, doesn't matter. You said that there were things expanding and things contracting.
I will show you.
Here something is expanding and contracting?
I will show you, yeah. So right now I just want to show you that if we are looking at just one material, so for example here we are looking just at one material, so if we look at just the actomyosin material, what we see is that there is this sharpening of the curvature and boundaries happening, but as we just said that there are two materials, so if we want to see both of them together, it looks something like this. So there is, in the purple, we have actin cap material, which is expanding outwards, and the other is the green material, which is the contractile network, which is contracting on itself and becoming thinner each time, and also going down in 3D.
Then it becomes thin because it goes down in 3 dimensions.
Yeah, because it's spread and then it contracts, and when it contracts enough, it goes down. Mm-hmm. So this bending basically, buckling basically happens.
Why does not it go up?
Well, it cannot go up because at the top there is the eggshell. So there's the eggshell at the top. So it's like a covering on the top. So if it cannot buckle up, it can only buckle down. So it buckles down. So interestingly, now that we know that this is what is happening, we can also appreciate the importance of this 2D network. So it is specifically important to define where the bending will take place, and it is important because this bending will basically define the compartment, each individual compartment, and we want them all to be uniform, all to be same, because they are going to be cells later on. So this is basically like the whole idea of my project, to understand that how this pattern formation takes place, and how this 2D pattern is formed, because this 2D pattern will later form the 3D pattern. And so now the question, how I'm trying to solve this pattern formation problem is by developing a mathematical model. Now initially this mathematical model will try to mimic what happens in a normal egg, and later on we will try to do some perturbation analysis both in the egg, rather in the embryo, and in the model. And finally, if we find some good mechanism, we can then apply them to other materials and understand them. So the beginning of my mathematical model happens by capturing one, this is the same image that I was showing you in the time-lapse images, and I just cropped it, just one ring, and then I try to see that there are nodes, like we can see these nodes. So these are basically myosin nodes, and these myosin nodes are connected to each other through an actin filament. So it's like there is one node, but we are viewing only node, we are not viewing the filament, so we don't know, but these are all perhaps connected to each other in some way. So what we see that, okay, let's just form this network, just a single network, and we try to mimic the inner diameter to be same, the ratio of the inner diameter and outer diameter to be the same as in vivo, so we know better that these things are not affecting the pattern. And then we define we give a unique ID to each of these nodes so that we can track them over time. And then we try to find their neighbors. So for finding neighbors, what I'm doing is like each node looks around itself in all directions and randomly picks out a particular number of nodes to make connections. So like 10 connections or 12 connections, we can vary that. Because we don't know what exactly is the number of connections in vivo, we can't see that. So once we make these connections, then this is like the initial configuration. So now we also put the cap inside, and we know that it's in the center of the whole system, so we put it there, and later when we will run the simulation, this cap will grow. And when it will grow, it will interact with these nodal network. So now is the time to run the simulation, but before that we also make all the connections of different individual rings, so that now we can understand what is the interaction dynamics and what is the dynamics of this growth together. And so when we run the simulation, the first thing is that we need to calculate forces on all the individual nodes. So for just to simplify it, I'm showing as an example just 4 nodes. So these 4 nodes will all pull on each other. But we want to calculate what is the force on this one node. So for this purpose, the force I say is proportional to how much myosin is inside this node. So this node may have this may be a small node having very little myosin, or this may be a big node having too much myosin. So if this is M1 and this is M2, the force would be basically directly proportional to M1, M2, and we just remove it by putting a proportionality constant. And this is in all directions. So we take a vector sum. And now another force that is being applied is through the caps. So the cap may apply force from different directions, and we need to have a net force for that as well. And once we have that, we sum both the forces up to find the total force on this particular node. Once we have that, we displace the node according to the force and the direction. And then as I just showed you, we keep on diffusing the cap as well. And finally, we print the output. And we print both the outputs for the cap and the nodes and repeat this process iteratively again and again and again and again to have the simulations. Now, just to have a test of if this makes sense, I just let the simulation run for a long time and see what emerges out through just having these nodes connecting to each other. And interestingly, I found that there are 2 types of dynamics that are coming out. The first dynamics is that this thinning takes place. So this is similar to what we saw in the embryo, so that it thins on itself. But later on, when it thins down completely, it starts to contract. And so this is an abnormal behavior that, of course, we do not see in embryo, but this is what we actually see. So this is encouraging. But then we want to do some perturbation, like to see if some variation of parameter is going to affect it. So this, before doing that, I'm just calling this change in shape at maturation. Doesn't mean anything, just like if there's a change in shape, I call it it's maturing. And so if I increase the myosin concentration on a node, so if I make the same node have more myosin, then I see that the maturation happens very fast. So it thins down and starts to contract very quickly. So this is like a proof of principle that, okay, it works. But we do not have any other forces in this particular simulation. We don't have interaction of different rings. We don't have cap expanding. So now I put it all. And what I see is something like this. So the different caps are expanding and they are pushing the myosin nodes, and it's something interesting is happening. But in this particular graph or image, what we see is that this red thing is the position of the node. So it's just giving positional information if there is a node there or it's not there. But it's not giving how much is the intensity. And to compare it with the actual system,
the intensity, you mean how much is going on?
No. It's the intensity means like
the concentration of myosin that
exactly.
is becoming more concentrated.
Exactly. So it means that if there is a node, then how much is the myosin in? It can be a node with just a little myosin. It can be a node with a lot of myosin. So, but we cannot know this from this graph because this is just giving positional information of whether there is myosin or there is not. So, but to compare it with the actual movie, where we see that there are like intensity variation and stuff like that, we plot another graph. I don't know how well you can see that, but what we see is that with evolution, the cluster starts to form. So, and these clusters like show this like circles forming out, just like we saw in the embryo as well, that we saw in the time-lapse images, that initially they were like random and then eventually they becomes more sharper. So we can see that, which is good. So that just gives that until now, what we can do is that we can simulate the contractile network of the model, and we can also simulate the expanding caps, the contracting myosin, and the formation of this sharp curvature that we were interested in. But this is all qualitative. But now we need some quantification done as well, so that we can compare if the behavior is similar to the embryo or not, and have estimation of the parameters which are more relevant. So to have a quantification, I needed some dimensionless parameters so that I can be sure that the dimensions are not playing some role in this. So the way I decided to do is like to measure the total area around a few nodes, a few rings, and divide it by the total area of the clearances. And we can do that in the system as well. So we calculate total area and clearance area in 3 different embryos. And in 3 different embryos, when we do that, we see that, okay, there is a similar profile. So now we can take a mean and have an idea about how it's happening. So we see that there is a 2-fold decrease in this ratio over time. And so now what I do is like I vary myosin concentration per node again on this whole system, and I see that there are variety of behaviors that are possible. But the interesting thing was like this very first one, which is like very low myosin, like 0.01 is the amount that I'm taking here. It's very constant, and interestingly, this is the time it corresponds to 500 stimulation steps. And this is the time when actin cap was expanding, but not really touching the cap. Sorry, touching the nodes. So this means that whatever is happening in these 500 time steps, it's happening just because of the myosin. And this is so this all will be abnormal for an embryo, because in embryo, whatever dynamics we are seeing here is because of the total effect and not just one system. So I decided to expand on this further. I'm not showing that quantification, but I expanded this little range to a great degree and found that 0.04 seemed to be a reasonable estimation of myosin concentration for the model, which will give output that is similar to this. So now taking this parameter, I decided to vary the density. So I made the density like 1%, 2%, 3%, 4%, up till 7%. Yeah.
Can we change density in experiment or something?
Yeah, I will come to that in just a minute. So, what happens here is that we can, when we vary this, we have a net estimate of 4% to be okay, because if we go 3% down and 3% up, there is not much difference in the dynamics, which means it's like similar. So this was encouraging as well, that we can simulate the actual quantitative dynamics by choosing a particular parameters. So now we decided to perturb the system, because that's our second aim. So the first aim was to mimic this in vivo normal dynamics, and the second aim was to actually perturb the system in silico. So when we perturb the system, what we're doing here is like we are increasing the concentration of myosin on a single node. And we increase it from 0.04 to 5 to like 0.5, and what we see is some abnormal stuff is happening here. The caps are expanding too much and they are colliding. So we thought that maybe this can happen in the embryo if we do something like this in the embryo. And here is where I come to your point, is like we decided to increase the abnormal myosin in the system, like in the embryo. So what is done here is in the embryo we inject, we do some gene perturbations so that the myosin is increased abnormally. And when the myosin is increased abnormally, we see that it's very different from what we see in the normal cell. Because in the normal cell, they are all very similar sizes. But here, some are very big and some become very small. And also, here we see that there are small punctals which are moving here and there. But here we have threads and cables running around, which is abnormal. And definitely this is nowhere to what we saw, which was like this, nowhere like this, because here what we were changing is just the mass and concentration on node and not the density. But here we see that both the density and the concentration seems to be changed. So we believe that that is one of the reasons for this abnormal behavior, that we are changing the density and concentration both, because that is the drawback of a biological system. You cannot do all the perturbations you want. When you do a perturbation, you may change 2 to 3 things at the same time. So it's not like a model, okay, I decide to change only density and I will keep the concentration same. No, when you really make the system to make more myosin, it will make more myosin in forms of more nodes as well as in form of more concentration per node. So, so like this is something that we are still like struggling to how to really mimic this phenomena, and so we decided to improve on this dynamics by going back to some literature. And what we see from the literature is that there are both chemical signals and mechanical feedbacks that happen, which decide that how much concentration of myosin will be there on a node. So what happens is, like if you strain the system a lot, if you put too much force on it, there will be more recruitment of myosin to maintain the structure and shape. So, and also this will make it from homogeneous to heterogeneous, that some places there will be more strain, other places there will be less strain, so more myosin, less myosin, a heterogeneous distribution. So just to explain that, we thought that if there is actin cap that is actually pushing on the nodes, what can happen is that the nodes which are in direct contact with the cap, they will feel more strain and develop more myosin. So there will be a gradient or heterogeneity that will develop, that one side which is in direct contact with the cap will have more myosin, and other side which is like not in direct contact but is indirectly affected will have comparatively less myosin. But this will change the formulation and other stuff, so we are still like working out on how to like really incorporate into the model. But this also brings us back to the cap dynamics. So if there are shape differences in the cap, they may have that one side of the nodes are more pushed while the other side is less pushed, and that may also indirectly affect the nodes. So we take a closer look on just the caps. So these are just the caps. So in this imaging, I'm only making the caps to fluorescent, and so I can just see how the caps are growing and expanding. And we see that there are these shapes which are not very smooth, and not circular, but not really with smooth edges. And eventually they become more smooth edges, but not to begin with. So I decided to like do something similar in my model by initially placing shapes which are not circular. So, but when I tried to do this, I saw that because I'm doing diffusion, as soon as I put an abnormal shape, but as soon as it starts to diffuse, it will try to smoothen it out, because that's the nature of diffusion. So I tried to take a shape which is completely non-circular, and the most non-circular shape I could think of was a triangle. So I just put a triangle in between and see how it will change with time. But strikingly, it also became circular from this side, but from the other side, where it was to begin with, like it was already extending into the myosin. So those myosin nodes were trapped inside the cap and making it less circular. But as the model keep on running, it became eventually completely circular. So here is when I'm like really in a fix at how to like really tackle the situation, which is that I know that in vivo actin is dendritic network. So it has uneven roughness on the edges, which eventually maybe on interaction with the node becomes smoothened out, and simple diffusion cannot make it like that. And so I'm thinking of other ways that can make it more heterogeneous. I would really welcome if you guys have any ideas of how it can be done, and we can discuss it in more detail later on that how we can make it more heterogeneous and dendritic and similar to what we see in vivo. But like that's a general summary for me, that I want to change the cap dynamics and formulation to explain the whole complexity of the interaction, and also I would like to expect a range of parameters that may actually suggest what is the model behavior, and maybe give another range of parameters that may be similar to some synthetic materials. So just to give what is the question I'm still struck on is that how do these materials interact so that the sharpness of the boundary gets stronger over time, and like what is the dynamics of that interaction, and for that I need to better model the nodes as well as the system. And with that, I would like to really acknowledge my supervisor for his constant advice, Professor Tony Harris for his constant advice and support, and my committee members for their advices and making model better and more complex. And of course, my lab members who helped me understand the biology, because I'm not from a biology background. I'm a electrical engineer from my background, and then I did my graduation in control, so this was completely new to me. So they helped me a lot in understanding the system, and so without that it would not be possible. And thank you all for listening patiently, and I would have any questions.